15 billion miles from Earth, in a place where the sun is no longer a sun but a pinprick, dimmer than Venus seen from your backyard. A 47-year-old spacecraft, running on less power than a household refrigerator light bulb, picked up a sound. Not a radio signal, not a transmission, not anything humans had put out there. A steady, narrow, almost musical tone, drifting in from the dark, at a frequency so faint that for years the engineers who built the instrument never believed it could detect anything this small. And yet, there it was, persistent, unbroken, a note being held by the void itself. The instrument that captured it, the plasma wave system aboard Voyager 1, was designed in the 1970s to listen for the violent, crackling turbulence of the outer planets, Jupiter's radio storms, Saturn's lightning. It was never engineered to hear what it just heard. And the astronomer who found it, going through archive data at Cornell University, sat with a file open on her screen for a long time before she told anyone, because the reading meant that the assumption underneath one of the most confident sentences in modern astrophysics, the assumption about what interstellar space actually is, was quietly wrong. Everyone assumed the space between the stars was empty, cold, silent, a near-perfect vacuum interrupted only by the occasional violent flare of a distant supernova. That's the picture in every textbook. That's the picture Voyager was built for. But the data quickly stopped fitting that story. By the time we're finished here, you'll understand exactly what those instruments captured, why the frequency itself is what makes it scientifically priceless, and why a single steady tone from an aging spacecraft may quietly rewrite how we estimate the density, the structure, and the survivability of the galaxy that surrounds our solar system. And I want to be clear from the start. The discovery isn't loud. It isn't cinematic. It's the smallness of it that's the story. Let me anchor the geography, because otherwise the numbers lose meaning. Voyager 1 launched on September 5, 1977. Right now, as of early 2026, it sits roughly 172 astronomical units from Earth, about 25.8 billion kilometers, or just under 16 billion miles. Light itself, moving at 299,792 kilometers per second, takes almost a full day to make the round trip. When Mission Control sends a command, they don't get a reply for nearly 48 hours. By November 2026, that gap becomes exactly one light day, a milestone no human-built object has ever crossed. And here's where things get interesting. Voyager 1 crossed the heliopause, the invisible boundary where the sun's magnetic bubble ends and the raw galaxy begins, on August 25, 2012. On that day, its instruments recorded a 40-fold jump in plasma density, essentially overnight. It had left the solar system, not the planetary neighborhood, the solar system itself, as physicists define it. Take a moment to actually picture that. A spacecraft the size of a compact car, built with 1970s electronics, CMOS chips, ferrite core memory, an 8-track era data recorder, sailing alone through a region no human instrument had ever occupied. No probe behind it, no probe ahead of it, just Voyager 1, and trailing a few years behind on a different trajectory, its twin, and it kept transmitting. Now, the anomaly. In 2017, in the archive stream of data coming back from the plasma wave system, something started showing up that nobody had put in the mission plan. A very narrow band of emission, a tone, sitting at roughly 3 kilohertz. Extremely weak. So weak that under any other conditions it would have been dismissed as background noise from the instrument itself. But it didn't go away. Month after month, year after year, the same faint tone was there. A plasma oscillation spacecraft was quietly logging into memory as it drifted deeper into the dark. The astronomer who spotted the pattern was Stella Kokacher, then a doctoral student in astronomy at Cornell. She and her collaborators published a finding in Nature Astronomy on May 10, 2021. And the title alone tells you how unusual it is. Persistent plasma waves in interstellar space detected by Voyager 1. Let me give you the actual measurements, because they make this tangible. Before 2017, Voyager 1's plasma wave detections came in bursts, loud, brief events triggered by shock waves from solar storms that had traveled outward for years and finally slammed into the interstellar medium. Those bursts were the only way scientists could measure the density of the material out there. Between the bursts, nothing. Silence. The instrument was functionally deaf. The new emission changed that. It wasn't a burst. It wasn't triggered by anything. It was just on. A continuous, low-amplitude oscillation, produced, the team concluded, by thermal motions of the electrons in the interstellar plasma itself. The gas between the stars was, in effect, humming. And here's the part that has no precedent. Everyone had assumed the interstellar medium was clumpy, patchy, turbulent, unpredictable, its density jumping wildly from region to region. That's what the burst measurements had implied for decades. But the persistent hum told a different story. Because the hum was steady, the density it implied was steady, which meant that this region of interstellar space, out beyond the sun's protective bubble, wasn't chaotic at all. It was uniform, structured, almost calm. And that's a problem, because if the interstellar medium is smoother than we thought, even in this one small pocket the Voyagers happen to be flying through, then the models we use to estimate how cosmic rays propagate, how supernova shock waves spread, how the galactic environment shapes the outer edge of every star system, including ours, are built on a foundation that just cracked. Quietly, in the archive of a spacecraft older than most people watching this. So, let's walk through what's actually happening physically, because the mechanism is where the story starts to feel almost eerie. Think of the interstellar medium as a very, very thin gas, but a gas made of charged particles, free electrons, bare ionized nuclei, not molecules bumping into each other like the air in this room. Something more like a fog of tiny magnets. When you disturb that fog, with a shock wave, with a passing burst of energy, with anything at all, the electrons don't just move, they ring, like a struck bell. The frequency of that ringing depends on exactly one thing. How many electrons are packed into a given volume? Density. Rehook. That's why the frequency matters so much. Read the frequency, and you've read the density. Not a computer model of density. The actual, physical, in situ measurement of how much matter is out there. Voyager 1 is the only instrument in the history of the species that has ever done this from inside interstellar space. Everything else, every telescope, every model, measures it from Earth's neighborhood through 15 billion miles of interference and infers. Voyager just listens, and the answer it's giving back is roughly 0.13 electrons per cubic centimeter. Down here, at sea level, you're breathing about 2.5 times 10 superscript 1 molecules per cubic centimeter. The interstellar medium is emptier than the best vacuum any laboratory on Earth has ever produced. And still, enough particles to sing. Now, I don't want to overstate this. The signal itself is minuscule. If you converted the power of the plasma hum into acoustic terms, it would be quieter than a snowflake landing on a pillow. But here's what makes it scientifically priceless. It's continuous, which means for the first time, humans have a live, uninterrupted, real-time monitor of the material that fills the space between stars. Not a snapshot, a stream. And the hum wasn't the only thing Voyager caught that didn't fit. Rewind to 2020. Voyager 1's magnetometer, a separate instrument, on a different boom, registered an abrupt jump in the intensity of the magnetic field embedded in the surrounding interstellar plasma. A pressure front. Something out there had pushed. The event was documented in the Astrophysical Journal the following year. Magnetic field and plasma density observations of a pressure front by Voyager 1 during 2020 in the very local interstellar medium. Scientific American summarized it more bluntly. Voyager 1 had entered a strange pressure front, a sudden increase in the magnetic field that scientists can't explain. And that layers onto an older mystery. When Voyager 1 crossed the heliopause in 2012, one of the most confident predictions in the mission, a prediction models had made for years, was that the magnetic field would shift direction. The sun's magnetic field runs one way. The galaxy's magnetic field, forged in supernova shock waves and older stellar generations, was supposed to run a different way. The moment Voyager punched through the boundary, the compass needle, so to speak, should have swung. It didn't. Both Voyager 1 and later, Voyager 2 reported that the magnetic field beyond the heliopause was running almost parallel to the sun's field, as if the galaxy, at this particular moment, at this particular angle, was somehow aligned with our own local bubble. Nobody predicted it. Nobody has fully explained it. So the pattern that's emerging when you stack these findings on top of each other is this: the space just outside our solar system is not the space we drew in the textbooks. It's smoother than expected. Its magnetic field points the wrong way. It has pressure fronts we can't explain. And it produces a steady, low tone that our best instruments were never designed to hear. And Voyager is, right now, the only witness. Now, here's an important bit of context, because I don't want to overstate what happened, and because the internet, predictably, has already overstated it for me. If you search for Voyager 1 online right now, you'll find headlines claiming the spacecraft has detected an alien signal. You'll find posts insisting NASA is hiding a message. You'll find people describing the plasma hum as a hum from something intelligent, or, in the more theatrical corners, as the sound of the wall of the universe. None of that is what the data shows. There is no alien signal. There is no message. The plasma waves are a natural, thermal, physical process, the same process, mathematically, that lets a struct tuning fork produce a tone. It's electrons oscillating, beautifully, unmistakably. Physics. But the actual concern in the science community is quieter than an alien signal, and, in a strange way, more disturbing. It's this: Voyager 1 is dying. In May of 2023, one of its 3 onboard computers, the Flight Data System, began producing corrupted, garbled telemetry. For months, Earth received a stream of nonsense. NASA engineers eventually traced the fault to a single failed chip, and by April 2024 they had rerouted around it, restoring communications from across 15 billion miles of vacuum using code decisions made in the 1970s. Then, on April 17th of this year, JPL announced they had shut down another instrument, the Low-Energy Charged Particles Experiment, to conserve power. Voyager 1 is now operating with only 2 active science instruments left, the magnetometer and the plasma wave system, the same instrument that captured the hum. So the real mundane, more disturbing danger isn't a fabricated alien transmission. It's that the single spacecraft giving us a live, unfiltered listen to the material between stars is running out of time. Its plutonium power source loses about 4 watt of output every year. Its thrusters are clogging with silica. Its data rate has dropped to 160 bits per second, slower than the modem of a mid-1990s home computer. Every additional year of operation is now measured in wattage, and when the last watt goes, so does the only interstellar microphone humanity has ever deployed. So back to what caused it. The answer to what Voyager 1 actually detected. The thing everyone initially assumed came from a shock wave or a solar burst or an instrument artifact turned out to be the interstellar medium itself, ringing at its own natural frequency, not something exotic. Something so fundamental, so pervasive, so quietly there that we had missed it for the entire history of astronomy. The gap between the stars is not silent. It has a resonance. And we know that now because a spacecraft older than the CD player kept listening after everyone assumed there was nothing left to hear. And the instrument that captured it, the plasma wave system, was indeed never designed for this. It was built to detect the roars of Jupiter and Saturn. What it's doing now, in the emptiness beyond the heliopause, is the equivalent of a stadium microphone picking up the sound of a single ant's footsteps in an empty parking lot. That it works at all is one of the quiet miracles of 1970s engineering. And the stakes, the reason this matters beyond the poetry, come down to this. If the interstellar medium is more uniform than we thought, then the way cosmic rays reach Earth, the way distant supernovae influence our climate, the way our sun's protective bubble is being compressed or eroded by the galaxy around it, all of it needs to be recalculated. Not dramatically, not apocalyptically, but precisely and precision in a field where our numbers come from a single spacecraft is a fragile thing. Here's what I keep coming back to. Voyager 2, launched 16 days before its twin, is following a different trajectory through interstellar space, angled below the plane of the solar system, sampling a different pocket of the galaxy. Its own plasma wave system is still running, and in the last few years, it has begun returning data that, in places, doesn't match Voyager 1's readings. Different densities, different field structures, different behavior of the hum, which means one of two things. Either the interstellar medium around our solar system is not uniform after all, and the calm Voyager 1 is hearing is a local pocket, a bubble within a bubble, and the wider galaxy beyond it is stranger and rougher than the hum suggests. Or the two spacecraft, drifting in silence at the edge of everything, are quietly telling us that the boundary of our home is not one boundary at all, that it has layers, that we haven't left yet, that the region we thought was outside is actually still a kind of shore, and the only way we find out which is if Voyager 1 keeps listening. For now, it still is